What are the types of Mosfet? I, Dr. Vandana Ranga, will like to discuss this with you. There are typically 4 types of Mosfets depending on the type of inversion layer. If at 0 gate bias, the channel conductance is very low and we must apply a positive voltage to the gate to form N channel, then this device is a normally off, that is the enhancement N type Mosfet. If an N channel exists at 0 bias and we must apply a negative voltage to the gate to deplete carriers in the channel to reduce the channel conductance, then the device is normally on, that is the depletion N channel Mosfet. Similarly, we have P channel normally off, enhancement and normally on depletion Mosfets. These are the 4 types of Mosfets which are available. They are all shown over here. The device across sections, output characteristics I versus VD and the transfer characteristics, that is ID versus VG, of the 4 types are shown in the figure. We note that for the normally off N channel device, a positive gate bias larger than the threshold voltage VT must be applied before a substantial drain current flows. For the normally on N channel device, a large current can flow at VG is equal to 0 and the current can be increased or decreased by varying the gate voltage. The discussion can be readily extended to P channel devices by changing the polarities. So these are the various types of Mosfets we have, that is the N channel normally off condition, the N channel depletion normally on condition, P channel enhancement normally off condition, P channel depletion normally on condition. And here we have the transfer characteristics, the output characteristics, the cross-sectional views of all the characteristics which we have. Now we discuss the threshold voltage control. One of the most important parameters of the Mosfet is the threshold voltage. The ideal threshold voltage is given by the equation which we have already discussed. However, when we incorporate the effects of fixed offset charge and the difference in work function, there is a flat band voltage shift. Additionally, substrate bias can also be influenced the threshold voltage. When a reverse bias is applied between the substrate and the source, the depletion region is widened and the threshold voltage required to achieve inversion must be increased to accommodate larger QSC. These factors in turn cause a change in the threshold voltage, where VBS is the reverse substrate source bias. The figure shows the calculated threshold of N channel, that is VTH, P channel VTP, Mosfets with N plus and P plus polysilicon and mid-gap work function gate electrodes as a function of the substrate doping. Assuming D is equal to 5 nanometer, VBS is equal to 0 and QF is equal to 0, mid-gap gate materials are those with work function of 4.61 electron volt, which equals the sum of the electron affinity Q chi and Eg by 2 of silicon. Precise control of the threshold voltage of Mosfets in an integrated circuit is essential for reliable circuit operation. Typically, the threshold voltage is adjusted through an ion implantation into the channel region. For example, a boron implantation through a surface oxide is often used to adjust the threshold voltage of an N-channel Mosfet with a P-type substrate. Using this method, it is possible to obtain close control of threshold voltage because very precise quantities of impurity can be introduced. The negatively charged boron acceptors increase the doping level of the channel. As a result, VT increases. Similarly, a shallow boron implant into the P channel Mosfet can reduce VT. We now take an example. The example is that for an N channel N plus polysilicon silicon dioxide silicon Mosfet with Na is equal to 10 power 17 per centimeter cube and QF by Q is equal to 5 into 10 power 11 per centimeter square. Calculate VT for a gate oxide of 5 nanometer. What is the boron ion dose required to increase VT to 0.6 volt? Assume that the implanted acceptors form a sheet of negative charge at the silicon dioxide interface. Here we discuss the solution. From the examples, we have seen that C0 is equal to 6.9 into 10 power of minus 7 farad per centimeter square. 2 side V is equal to 0.84 volts and VFP is equal to minus 1.1 volt. Therefore, with VBS equal to 0, VT is equal to VFB plus 2 psi B plus 2 epsilon S Q Na 2 psi B under root. This whole thing is under root divided by C0. So if you put the values, this comes out to be 1.1 plus 0.84 plus under root of 2 into 1.1, 11.9 into 8.85 into 10 power of minus 14 into 1.6 into 10 power of minus 19 into 10 power of 17 into 0.84 divided by 6.9 into 10 power of minus 7. This thing is under root. This is equal to, if we calculate the values, it comes out to be minus 0.02 volts. The boron charge causes a flat band shift of QFP divided by C0. Thus, 0.6 is equal to 0.02 plus QFP divided by 6.9 into 10 power of minus 7. FB is equal to 0.62 into 6.9 into 10 power of minus 7 divided by 1.6 into 10 power of minus 19. This is equal to 2.67 into 10 power of 12 per centimeter square. We can also control VT by varying the oxide thickness. Threshold voltage becomes more positive for an N-channel MOSFET and more negative for P-channel MOSFET as the oxide thickness is increased. This is simply due to the reduced field strength at a fixed gate voltage for a thicker oxide. Such an approach is used extensively for isolating transistors fabricated on a chip. The figure shows a cross-section of an isolation oxide, also called field oxide, between N plus diffusion and N well. Details about the field oxide formation and well technology are already discussed. The N plus diffusion region in the source and drain region of a normally the gate oxide of MOSFET is much thinner than the field oxide. When a conductor line is formed over the field oxide, a parasitic MOSFET called the field transistor results with the N plus diffusion and N well regions of the source and drain respectively. The VT of the field oxide is typically of the order of magnitude larger than that of thin gate oxide. During circuit operation, the field transistor will not be turned on. Consequently, the field oxide offers good isolation between N plus diffusion and N well regions. We now take an example. For an N-channel field transistor with Na is equal to 10 power of 17 per centimeter cube and QF by Q is equal to 5 into 10 power of 11 per centimeter square, calculate VT for a gate oxide, that is the field oxide of 500 nanometer. The solution is C0 is equal to the epsilon oxide divided by D. This is equal to 6.9 into 10 power of minus 9 farad per centimeter square. And we have 2 psi B is equal to 0.84 volts and FB is equal to minus 1.1 volt. Therefore, from equation we have VBS equal to 0. So, VT is equal to VFB plus 2 psi B plus under root of 2 epsilon SQNA 2 psi B divided by C0. So, if you put the values, it becomes 1.1 with a minus sign plus 0.84 plus under root of 2 into 11. So, this comes out to be 24.12 volt. This is the value of the VT. So, we now discuss the cross section of a parasitic field transistor in an N-well structure. This we have shown over here. So, the substrate bias can also be used to adjust the threshold voltage. According to the equation, the change in threshold voltage due to substrate bias is delta VT is equal to under root of 2 epsilon S QNA divided by C0 in brackets under root of 2 psi B plus VBS minus under root of 2 psi B. If we plot the drain voltage, drain current versus VG, the intercept at VG axis correspond to the threshold voltage. Such a plot is shown and for 3 different substrate biases. As the magnitude of the substrate VBS increases from 0 volt to 2 volt, the threshold voltage also increases from 0.56 to 1.03 volt. The substrate effect can be used to raise the threshold voltage of the marginal enhancement device. VT is nearly equal to 0 to a larger value. Now we discuss another example. For the MOSFET, which we discussed earlier in the previous example, with VT of minus 0.02 volt. If the substrate bias is increased from 0 to 2 volt, calculate the change in threshold voltage. So, we have from the equation which we have discussed over here, that is delta VT is equal to under root 2 epsilon S QNA divided by C0 under root of 2 psi B plus VBS minus under root of 2 psi B. So, this delta VT is equal to under root of 2 epsilon S QNA divided by C0 in brackets 2 psi BS plus VBS minus 2 psi B. So, this change delta VT has to be calculated. So, this value if you substitute, that is under root of 2 into 11.9 into 8.85 into 10 power of minus 14 into 1.6 into 10 power of minus 19 into 10 to the power of 17 divided by 6.9 into 10 power of minus 7. So, this is equal to under root of 0.84 plus 2 minus 0.84. So this value comes out to be 0.27 into 1.6 minus 0.92. This is equal to 0.21 volts. Another way to control VT is to adjust the work function difference by choosing an appropriate gate material. A number of conducting materials have been proposed, such as tungsten, tin nitride, and a heavily doped polysilicon germanium layer. In deep submicron device fabrication, control of the threshold voltage and the device performance becomes more difficult because of the geometric effects encountered in device scaling. See the discussion in the next section, which we'll be discussing in the next class. We use the other gate material to replace the conventional N plus polysilicon could make a device design more flexible in deep submicron fabrication. So this is all we have to talk today. Thank you.